Construction 3D printing, or C3DP, utilizes large-scale extrusion-based additive manufacturing to deposit cementitious material layer by layer. The fundamental physics demands material thixotropy. The mix must flow easily under shear stress during pumping, but immediately develop sufficient yield stress upon deposition. This rapid yield stress development is necessary to support the weight of subsequent layers without deformation or collapse. C3DP eliminates the need for conventional formwork, significantly reducing material waste and labor time associated with casting concrete. Typical layer heights range from 10 to 50 millimeters, with extrusion widths between 50 and 150 millimeters, precisely defining the wall geometry. The material must transition from a viscous fluid to a self-supporting solid in seconds. C3DP systems are categorized by their operational scale and mobility, directly impacting project feasibility and construction speed. Specialized cementitious mixes, often incorporating supplementary cementitious materials like fly ash or slag, are engineered specifically for printability. Controlled rheology is critical, balancing three conflicting requirements: pumpability, buildability, and open time. Pumpability ensures the material flows through the delivery system without segregation or excessive pressure loss. Buildability refers to the material's capacity to resist deformation under load, requiring rapid development of early compressive strength, typically within minutes of deposition. Open time is the duration the material remains workable before initial setting, which must exceed the total printing time for a continuous layer to prevent cold joints. Chemical admixtures, such as superplasticizers, reduce viscosity without adding water, enhancing pumpability. Accelerators precisely control setting kinetics, ensuring the rapid strength gain required for buildability. Two primary C3DP systems dominate the field: Gantry systems and Robotic Arm systems. Gantry systems use a fixed, rail-mounted frame, offering high precision and scalability for large, single-story footprints. However, they require significant setup time and are less mobile. Robotic arm systems offer greater flexibility and reach, often mounted on mobile platforms suitable for complex geometries or existing structures. These systems typically sacrifice some positional accuracy compared to gantry setups. Printing speed is quantified by the volumetric deposition rate, measured in cubic meters per hour. Current commercial rates for structural walls range from 0.5 to 2.5 cubic meters per hour. This rate is limited primarily by the material's curing rate and the required buildability time rather than the mechanical movement speed of the printer head itself. The primary structural challenge in C3DP is material anisotropy, where mechanical properties vary significantly depending on the stress direction relative to the print layers. Tensile strength and flexural strength perpendicular to the layers, known as interlayer bond strength, are substantially lower than parallel intralayer strength. This weakness results from the formation of cold joints between successive layers, where hydration products do not fully interlock across the interface. Failure analysis frequently shows crack propagation initiating along these weak interfaces. Improving interlayer adhesion requires minimizing the time gap between layer depositions to ensure wet-on-wet printing. Alternatively, chemical bonding agents can be applied to the surface of the previous layer immediately before the next is extruded to promote chemical fusion. Printed concrete, like conventional concrete, possesses high compressive strength but inherently low tensile strength, necessitating reinforcement for structural applications. Traditional steel rebar cannot be extruded and must be integrated either manually into pre-printed cavities or robotically placed during the printing process. Fiber-reinforced concrete, or FRC, offers an alternative, utilizing short, dispersed fibers such as glass, polymer, or steel within the mix. FRC enhances ductility and mitigates crack formation, particularly improving the tensile capacity across the cold joints. For multi-story structures, vertical load paths require dedicated reinforcement. Post-tensioning cables or vertical steel rods are often required, running through dedicated vertical channels left open during the printing process to be tensioned or grouted later. Three-dimensional printed walls are typically designed with internal cavities, serving dual purposes, reducing material consumption and accommodating utilities. Electrical conduits and plumbing lines are routed through these voids during or immediately after printing, minimizing post-construction cutting. Thermal performance requires the integration of insulation materials to meet energy efficiency codes. This is achieved either by injecting lightweight materials like foam or perlite aggregate into the cavities post-printing. The superior method is co-extrusion, which uses multiple nozzles to simultaneously print the structural cementitious shell and an insulating core material. Co-extrusion ensures continuous thermal breaks within the wall cross-section, significantly minimizing heat transfer and improving overall R value. Construction three-dimensional printing technology extends beyond residential construction into civil infrastructure, leveraging its ability to fabricate complex, non-standard geometries without expensive custom formwork. Applications include printing bridge components, culverts, retaining walls, and specialized noise barriers along highways. Mobile C3DP systems are particularly valuable for remote or hazardous environments, reducing the need for extensive on-site labor and improving safety. Furthermore, three-dimensional printing is used to rapidly produce custom molds for precast concrete elements. This capability allows for rapid prototyping and mass customization of infrastructure components that would be cost-prohibitive using traditional casting methods, accelerating project timelines for complex designs. Regulatory acceptance is the current bottleneck for widespread adoption of three-dimensional printed construction. Building codes are typically prescriptive, defining minimum requirements for established materials and methods. Three-dimensional printed structures often require performance-based certification, necessitating extensive testing to demonstrate structural equivalence to conventional construction. Required tests include load-bearing capacity, fire resistance according to ASTM E19 standards, and seismic performance verification. Standardization of material mixes and printing protocols is essential for achieving scalability across different jurisdictions. Future developments focus on achieving certification for multi-story structures and integrating automated quality control systems such as laser scanning, verifying layer geometry, dimensional accuracy, and structural integrity in real time during the printing process, providing necessary data for regulatory approval.